Oh, that's good. I would prefer if people could be more interactive and they do actually respond. And that way, I think we would be able to make more sense of this talk. I'm
Okay.
sharing my screen. I hope everyone can see the screen.
Yes.
Okay, good. So today we are going to discuss on how linear algebra can be applied, and I assume that is what has already been done in some of the lectures earlier. And since this is teachers enrichment workshop, which which is discussing various uh, aspects of linear algebra, and the applicative aspects of linear algebra are certainly worth discussing, because in our college education, that's what is missing, and students have lots of questions. And in order to enable us answer those questions, and also in order to enrich our understanding of the ground understanding of mathematics, it's good to know such applications. So thank you. I begin with that. And the title of this talk is From Linear Algebra to Google. And somewhere graphs will be in the picture. So the way we will be connecting Google is graphs actually. And there is linear algebra which comes. Okay, so before I actually start, let me just show you some picture. And the purpose of showing this picture to you is to ask you a question. What is the picture? Can someone among the participants guess what is this picture? Looks quite beautiful. Any response? If someone has seen such a picture earlier, you can make any guess. Okay, no guesses. Then I will ask another question. What is this picture? At least this picture is more familiar to us than the previous picture, right? So what is this picture? Any guess? Some participant? Oh, okay, that's very good answer. It's not quite correct. Someone says electricity. Okay. World map. Okay. Okay. Nice. Nice. What else? You can speak also if you want. Okay. Two answers I got. Okay. Let me come back to the answer of the first question. The first picture is actually the picture of the internet. If you look at these two people, Dodge and Kitchen, they're actually cartographers. So what they do is they convert a data into a map, into a graph, into a picture. And they have created one very beautiful book. I think now it's quite old, something like 15-year-old book, 2005 or 2004. It's called Atlas of Cyberspace. In that book, they have many the internet-related data, which they express through pictures. And this is the picture of the internet, not today, but it's actually almost 15 years ago. So you can see internet is a complex system. It's a complex graph. There are so many nodes and things are interconnected to each other. Yeah. And this picture is actually Facebook Friends network. It's not the electricity network or the world map. It surprisingly looks like world map, which it is not. What is done is that if you put two geographical locations, if there is a friend, if there's a Facebook friend between those two locations, you connect it by an edge. You just connect it by a straight line, and in the process, you will end up getting a world map. That's quite interesting. It's almost world map. For example, if you just imagine there are two friends, it's very likely that you have more Indian friends than say American friends or European friends or the Japanese friends, right? So there will be more edges which are connecting India within the country, or that's the case with other countries. But interestingly, as you can observe in the map, is obtained by Paul Butler based on certain Facebook data. I think this was some 50 8 lakh people's data on Facebook. China is clearly missing, right? So had it been the world map, China would not be missing. So this is actually Facebook map, but the surprising thing that it encaptures a lot of demographic information, lot of information about the geographical locations of Facebook users. So that's something quite interesting. Okay, so I continue. And if you want to know the complexity or the how large the internet is, this is the data which I just took today. You could be interested in this website called worldwidewebsize.com. So this website, worldwidewebsize.com, they update every day information about many web pages which are indexed by many search engines, say Google or Bing, any other search engine. So here on the x-axis, you can see the date. So I got this information today. So this is around the 25th November or plus. And here you have number of web pages. How many web pages are there which are indexed by Google? And you can see this has been in the range of 54 billion, right? So roughly, let's say somewhere here, there are some 55, 56 billion web pages, and that would be multiple times. It's much more than the population of the world. The world population should be around 7.5 billion, and this is something like 7 times more. So that's huge, huge number. The number of humans is much lesser than the number of web pages, and that's where we're supposed to do certain search, internet search. So therefore, internet search becomes a complex phenomenon. Another estimate of how large is the internet. There's a very interesting website called internetlivestats.com. So this data itself I took today only. And if you go on this website, there will be a counter. They have a way of estimating how many internet users are there, how many emails have been sent today, how many tweets have been made, how many Instagram posts have been done, and so on, how many Google searches have been made, and all that. You can see it's a complex thing. It's huge system to handle. Okay, so as I just try to make the background, there are about 55 billion web pages. Of course, every search engine has a different number because not every search engine will be taking an indexing of all the web pages. So let's say for Google, the number is estimated to be 55 billion. So that's the challenge, how to extract a meaningful and relevant information from these web pages. That's a big challenge. And of course, we know the answer. We have to use search engine. We have to carefully use search engines in order to get what we want to get out of internet. Yeah. And as far as Google is concerned, it handles huge number of queries. So estimates have been made which are always 50,000 plus. Even 10 years ago, the estimate was like 12,000 queries per second. But now there are many websites which make an estimate of even 70,000 per second. Let's say 50,000 or even more per second is a good estimate. That's a huge number. And how does the query, Google query travel? So we give a query and then just in a number of seconds, it returns the result. So what is happening behind is what we are going to see today. And in the end, something about Facebook is also what I will say. And both the examples of Google and Facebook are going to be interesting applications of linear algebra. So I hope up to this point, I am with you and you are with me. Yeah. Any query, question up to this point? Yeah. Okay. So I continue and I try to explain what is this. So this is also taken from the Google website. Here's a query. I am asking, I have some questions, I have some search queries, and I have to get its result. Of course, that's a purpose. So how do we try to search for our terms in a book? right? Every book has an index. In the end, there is the list of words, and from those words, we can go and see what are the relevant page numbers, and that's how quickly we can accomplish our search in a book, normal usual book. Google also has similar principle, but then it is augmented by a lot of mathematical inputs. So when we send our query to Google Web Server, these queries further go to what are called index servers. So index servers, you can imagine that this is the index which is there in the end of the book. So the word and page-wise words are mentioned. From index servers, it goes to doc servers. So what are doc servers? Doc servers have some clip, some basic information about that web page. So if you make a Google search along with the link, it will also have some small description of the page. So doc servers have that information. Okay. So from index server, you can go and glimpse into what will happen if what kind of content you will be seeing if you click that particular link. So this link is actually associated comparing with index is there in the end of the book. And once you have so many search results, then the whole bunch is returned to the user and user gets that answer. And where is the mathematics? Where is the linear algebra part in this cycle? The linear algebra part that I'm going to describe today is going to occur in this particular arrow. Okay, let's actually do a Google search. So I did this Google search for IIT Jodhpur, and that's how many 93 lakh results were returned by Google to me in just 0.67 seconds. Okay, that's amazing. But you see, the word IIT Jodhpur will be coming in so many websites, right? There could be some education websites, some tuition coaching websites where IIT Jodhpur, the word itself comes much more than what IIT Jodhpur contains, right? The website. So how did it recognize that out of these 93 lakh search results, this is the most important? Because when we do Google search, whatever are the answers, whatever is the search queries output, we will look in the first page, second page, third page. Beyond that, we won't see. We are not going to see, say, 1,000 entry. We are not going to certainly see 93 lakh last query, right? Last answer. So that is the point. How does Google know that it should rank all the search results in such a way so that the most relevant ones actually appear before the other page? Like that's where I'm saying that's where our linear algebra is playing an extremely important role. Okay. Okay. So that's what I explained. So for search engines, the result is that there are so many search results. How to present them back to the user? Of course, the common sense the thing says that show important pages first, but that is precisely the problem. How to realize that which page is more important and which page is least important. And that's where linear algebra is going to come up. So that's the question, right? How to rank web pages in the order of importance. Some of the possible answers could be count the frequency of the search query. So if I type IIT Jodhpur, I present the web page which is having maximum number of terminology IIT Jodhpur. That's a very preliminary answer because it's easy to no, it is easier to manipulate because I can make a web page which has so many IIT Jodhpur, and I will become the first ranker for Google query. Certainly, Google will not like such an approach. Or you find some kind of way of realizing what page is more popular, right? The popular pages could be up in the query, so they could be appearing on the first page, and in subsequent pages, less popular results could be coming. But there is even much interesting concept, which is what is called hit search idea. HIT stands for Hypertext Induced Text Search. Hypertext Induced Text Search. What is hypertext? The link, the clickable links, they are hypertext. I can, of course, there is a text because I can read it, but I can also click it. And that is what is hyperlink. So the one of the ideas which one of the earlier persons who was working on HIT search idea, John Kleinberg, he was quite young that time. He said that, okay, you count which page is referred more by another important page. Okay. So what are other important pages which are, if some important page is referring to another important page, perhaps that is a good indicative of what is actually important. Right? And I will elaborate this point. And if you see the way, so what is the idea? So the idea which is there in the hit search concept is that you explore the hyperlink structure of internet. So there are websites. Just assume that all these are so many web pages. Okay, and you see some web page which is referred by another web page. So this is kind of recommendation. This web page D is giving recommendation to web page A. So if there is a hyperlink which is originating in D and which says A, go to A for this particular thing, that means it is giving its recommendation to A. And that's where D is sharing its reputation with A. That's how we are going to read it. D is sharing its reputation with A. And similarly, if you see B, there are so many web pages which are sharing their reputation with B. But if you look at C, there is only one web page which is referring to C. No other, right? There is only one web page which is having a hyperlink which points to C. But since B itself is so important, see, you can see B is so important. Therefore, the recommendation value of B is higher, and just by the fact that it is referred by only one website, one web page, C itself becomes quite important, quite uh, higher in the rank structure. So I hope this point is clear to us. And on this idea, we are going to build up certain equations, and we will see where lies the solution. So this is the most important slide. I hope you have gotten the idea here. So we are exploring the hyperlink structure of internet. Am I clear on this point? Some feedback can be given to me. All
Yes.
these are web pages, and what we are exploring is hyperlink structure. So this kind of recommendation. Huh? Okay, I'll come back to that. So Google story, as many of us would know, dates back to now 22 years, 1998. This was the earlier version of Google Beta, the testing version. 1998, yeah, you can see that. And these are the two people, two young men that time, Larry Page and Sergey Brin, who start exploring hyperlinks, the concept of hyperlinks and how the link analysis can be done over the internet. Okay. And based on their ideas, very soon the Larry Page patented this algorithm, this method, PageRank, and now it's called PageRank TM trademark method. The PageRank, the algorithm that I'm going to explain you, the word page comes actually from Larry Page, not from the web page. Yeah. And in those explorations of finding out a good hyperlink structure and its interpretation, one of the connections is actually from India, Professor Rajiv Motwani, who was professor at Stanford. He was an alumni of IIT Kanpur. he was native of Jammu, went to IIT Kanpur. After that, he moved to MIT for PhD, and Stanford he was teaching. He was one of the earlier co-authors of these people. And if you go to Sightseer, the website that stores many abstracts in the area, you can see the one of the very first paper on the topic, which says what can you do with a web in your pocket. Actually, it's quite readable paper, and somewhere they are appreciating that over the last 1 decade, how much of the uh, space, for example, the computer power, disk capacity, all those things have increased. And this was 1998. But if you compare 1998 with the day today, you can just imagine how much of the progress we have made in that direction, right? And now 128 GB you can easily put actually in your pocket. So this was quite interesting topic, quite interesting paper that time. And all the idea behind Google search algorithm lies in this. Yeah. So this is work. Okay. So I explore the hyperlink idea, and along with that, I will also present to you certain equations. Yeah, and then whatever you have done in this workshop so far with linear algebra, you will be able to appreciate. Particularly, the concept of eigenvalues and eigenvectors is what you are really going to appreciate. Okay, so these are two principles here on the basis of which we are going to set up our equations, set up how to actually rank pages, right? The first principle is that important pages are the ones which are recommended by other important pages. So other important pages, if they recommend someone, then that person becomes or that page becomes important. However, if there is a page that is recommending many other pages, that means it is very lenient in giving its recommendation, then the value of its recommendation goes. So I might be very important from some perspective, but if I am recommending everyone, then the value of recommendation is going to come down. So I hope these two principles are clear. Just give me some feedback on this. Yeah. So what determines important? If you are recommended by other important pages, and second, if you are recommending too many, then the value of the recommendation is going to come down. Yeah. And this is the equation, right? So what is RPI? What is RPI? P1, P2, P3, just assume those are web pages, right? So there are n web pages. So what is RPI? RPI is rank of highest page. Rank meaning what we are doing is out of 1, we are giving a score. Okay? Giving the score out of, and RPI is the score obtained by highest page in that ranking. Okay? So what is the ranking of J? So J's ranking depends on what are other pages I which are sharing its weight with J. Okay. So suppose, so here BPJ denotes what? This is a set of all those web pages which are recommending J. So I is a web page which recommends J. Okay. Recommends meaning in terms of hyperlink. So whatever is the credibility of I, that is going to be shared by not PI. This is number of recommendations given by I. So that it will come down. So I'm dividing because of the second principle which I had. Recommendation value will come down if there are so many recommendations which are distributed by me. And RPI is indication of the importance. This is the basic equation which I have. I hope this point is also clear to you. For each page, this is how I can obtain. I can obtain ranking, but there is a fundamental flaw with this. equation because I'm using RPI to compute something about RPI. So this is kind of iterative loop because I actually don't know the value of RPI. I don't know what is the ranking of each page. So by ranking, I mean score out of 1. Out of 1, how many points are you going to give to this page? So it seems we are going in a finite loop because I'm determining something in its own terms. So what's the basic idea to resolve it? And that's where the Sergey Brin and Larry Page came up with very nice rescue scheme. They said in the beginning, let's assume everyone is equally important. So this calculation, rather than doing it in one go, let's do it in multiple rounds. Okay, in first round, everyone is equal. And then explore the hyperlink structure using this equation. And in multiple occasions, in multiple equations, you see how things are converging. That's the basic idea. So RK plus 1 denotes the ranking after K plus first round. And to calculate the ranking of K plus first round, what do you use? You use previous round score. So you should use RK. Yeah. And in the beginning, everything is having rank 1 by n, where n is the total number of pages which you want to, which are there in your system, which are there in your internet. So this is absolutely brilliant idea to start with a neutral approach, and then based on hyperlink structure, you update your ranking. And then you hope that as K becomes larger, this converges. Yeah. So good. So this not PI is number of pages which are recommended by P, which are recommended by PI. PI is a page. Okay. So suppose P10, the web page number 10. Whatever is its value, it is shared among how many? Among not PI many web pages. So these are number of web pages which are recommended by PI. Yeah. So is that clear, or should I say more on that? You can give me feedback. Okay, good.
Devanshu is asking what is mod of PI.
Yeah, so I have answered that. So this is
Okay.
the number of web pages which are recommended by PI. Yeah. Okay. Now let me try to write this equation. This equation in terms of linear algebra. Okay, in terms of matrix multiplication. How do I do that? I treat 1 mod PI, those things as coefficients, like in matrix coefficient. So I'm thinking of a matrix, I'm calling it H, whose ijth entry is Hij. And what is Hij? 1 by mod Pi if Pi recommends Pj. And otherwise it's 0. Because if I have this definition, I can express this equation in terms of a matrix multiplication. Okay, how? Okay, so after kth round, I'm assuming that first page has rank that is score RKP1, second page is having RKP2 like that. And this T is for transpose because I want to write things as a column vector. Okay, the transpose. So I'm writing down all the scores of all the pages as a vector column. And this VK is what I am updating in every round. So K is kth round. And as we have seen, in our first round, we were neutral. Everything was 1 by n. Everything was equally important or unimportant by 1 by n. That was our ranking. That was our score out of 1 that we gave to all the wastage. And after that, this distribution of 1 started based on hyperlink structure. Yeah. So this is the this is the ranking, the entire data VK. This is what I should observe. How do you go to the next round based on the previous round? This is just the matrix multiplication. or the linear transformation H you apply on the column vector Vk. H is this matrix. So this equation that I have written is just matrix expression. This is the matrix multiplication H into Vk. This is the matrix multiplication notation of the same set of equations, this one. So this equation and the other one, which is in terms of matrices, there is no difference. It's just the notation is different. That's all. Okay, because my coefficients are coming from 1 divided by mod pi, right? So here also my coefficients are coming from 1 divided by mod pi, and these are vectors. These are vector entries. The ith entry in the vector Vk. Okay, and I just have to keep putting H again and again, and I just have to hope that this sequence converges. Yeah. So that's what let me do. So consider this as an internet. This is my internet consisting of 6 web pages. Okay. What is hyperlink matrix in that context? Let's go to the page to the first row. Yeah. If I go to sorry, if I go to first row, what are the web pages which so one, if you go to one is referring 2 and 3, right? One is recommending 2 and 3. So one is giving, therefore 2 recommendations. Value of its recommendation therefore will be half. So it's half. Other places you put 0. And what about web page 2? Not giving recommendation to anyone. So it's 0 throughout. Forward web page 3. So it is giving recommendation to 2, 1, and 5. So 3 is giving recommendation to 1, 2, and 5. So for 3, 1, 2, and 5, fifth column, the value of the recommendation will be 1 by 3, 1 by 3. Others it's 0. So this is precisely the definition of this matrix, right? Hyperlink matrix. So the entire hyperlink data I have summarized as a matrix. Is it fine with us? Yeah. So just the matrix multiplication is what I have used so far in this notation. Okay. Now I have to make some correction. What is called stochasticity adjustment, and so the idea of having this is so that it allows us to apply certain theorems which are for what are called stochastic matrices. So you remember the second row was 0 throughout. Why was it 0? Because 2 refused to recommend anyone. So rather than say that 2 is not recommending anyone, let's say that 2 is recommending everyone equally, including itself. So what I do is, in place of 0, I put 1 by 6, 1 by 6. What's the advantage? Well, this approach has changed because saying that it is not recommending everyone, we have said that it is recommending everyone equally. But the advantage that we actually obtain is in terms of the applicability of certain mathematical theorems. Okay, so that our calculations become doable. Okay. There is one more adjustment which is actually done by Google. So what it does is it is called primitivity adjustment. What are we assuming in this model so far, the hyperlink model, that the surfer, the person who is surfing the internet, is just following our hyperlink structure. But what may happen is that with a certain probability, the random surfer may actually use some other judgment to go to some other website. That human judgment may come, or maybe the person gets bored and with some other judgment gets to some other website, and that's also a statement on what is important, what is not. So there is something called damping factor, meaning This model is going to be used with certain probability by the user, but user may also choose randomly some other website. Okay, so to make that adjustment for certain value of alpha, which is less than 1, some kind of adjustment is done by the Google, and it's called damping factor. The value of damping factor which Google uses is around 0.85 and it's quite stable. But it is subject to updates depending on their analysis and observation. So rather than using the hyperlink matrix which was there after stochasticity adjustment, you actually use Google matrix. After taking an input from what is called random surface model, and then what do? You replace H by G in this session. What is this information, this equality? This equality is coming from those two principles. If the important person recommends you, then your value goes up. But if an important person gives so many recommendations, then the value of the recommendation of that person goes down. So those two things are therefore captured along with stochasticity and primitivity adjustment in this equation. Okay. And now what we do is we keep iterating on this. So we, after kth round, after k plus first round, after k plus 2 round, and therefore we get vectors after each round. And the hope is that the sequence of vectors converges. So once it converges, you declare, okay, these are the value attached to the different graph page. Okay. So the vector v to which the sequence converges is going to be the page rank vector. That is the basic principle, and let's analyze it by one more level of depth. And the first question, of course, should come that why should the sequence of vectors converge? Okay. So what I did for this particular internet, I wrote a C program. So I did that long back, but I retained the results of that. Okay, so here is our sample internet, and let me actually do this analysis, which is a iterative analysis of all the page ranks. So this is my sample internet, and as we had decided, after 0th iteration, that means to start with, we have 1 by 6 value attached to all the web pages. Yeah. And for that particular matrix which I have, which is corresponding to this, I have shown you already. So after each iteration, I'm showing you what are the results. So do you see some convergence already? So I think I did for 25 iterations. Yeah. So do we realize some page is more important here? Do we declare it's a convergence? Okay. So in this particular example, it seems it converges. Yeah. So although convergence is not something which you can see visually, it has to be proven. Huh? But nevertheless, in this case, let's assume that this is the outcome, and according to this analysis, out of 1, the web page number 1, 2, 3, 4 gets 0.37 score. So 4 is more important, it seems. And after that, it is 6. Okay, 4 and 6 are more important. Actually, incidentally, they are referring to each other. Okay, just from the structure, you cannot make out much. But when you do this mathematical calculation, you can actually make out things based on your two principles, which I had already stated. So what is to be analyzed? Therefore, see, let's go back to those equations which this one, right? So suppose it converges to V. So this rank vector, suppose it converges to V, and in that case, GV will be equal to V. Yeah. And what's the meaning of GV equal to V? That means V is an eigenvector for the matrix G, and the corresponding eigenvalue is equal to 1. Right? GV is equal to V. So eigenvalue is 1 and V is the eigenvector. So therefore, all this discussion can be related to the discussion on eigenvalues and eigenvectors. And you have already seen what eigenvalues and eigenvectors are. So this is eigenvalue is that after a linear transformation, if you can get a direction along which the effect of transformation is just scaling, then that particular vector is called eigenvector, that particular direction, and the stretching factor is called eigenvalue, right? That's what you must have already seen in the first week of this program. Yeah. So eigenvalues and eigenvector you are already comfortable with. And what we want here is some eigenvector of eigenvalue 1. And that's what is required by the equations set up by Larry Page and Sergey Brin in their algorithm. The point is, why should the convergence happen? And incidentally, all that convergence is guaranteed by what is called Perron-Frobenius theorem, which was much older than the Google algorithm. Google is 1998. This theorem is about 1908. Yeah. So what does it say? So it says something which is as if this theorem is made for Google just even 90 years before, the Google. So it says that if you take a non-negative matrix, meaning all the entries are non-negative, so that's what a Google matrix is. If you take a stochastic matrix, stochastic meaning all the rows add up to 1. Okay, and that's what was happening because 1 was being distributed among all the web pages. And there is one more assumption actually, irreducible matrix. So irreducible matrix I have not explained, but it can be explained through what are called strongly connected graphs. It turns out that Google matrices are actually irreducible. So let's assume that. So for matrices such as Google matrix, what is statement? Statement is the eigenvalues. If you talk about for any such matrix, these are going to be complex numbers to start with, right? So maximum modulus of an eigenvalue can be, well, it has to be 1. That's what the theorem says. Okay, so among all the complex eigenvalues, the maximum modulus is going to be 1. And actually, there is only one eigenvalue with modulus 1. There is only one complex number which occurs as eigenvalue for such a matrix, and its modulus is 1. Modulus is that the real part times z bar, right? Square root of z bar, z some complex number. In fact, the eigenvalue is 1. So what it says is that there is an eigenvalue 1 for any such matrix. And that's what we wanted, right? And further, there's a unique vector which is called Perron vector for which the eigenvalue is 1. Therefore, what does this theorem say? Okay, as if this is made for Google matrix, right? So the theorem says that if I take a Google matrix, then there indeed exists a V vector for which V is Google matrix times. And that is what we can actually take as page rank vector because it has to be unique. Okay, so that is going to be page rank vector for our analysis of the ranks that we want. Okay, so Perron-Frobenius theorem is a theorem which dates back like 90 years before Google, and it has all the relevant requirements which are there to solve the problem of Larry Page and surgery, the patient algorithm. And one can actually write some algorithms for actually finding out what that page rank vector is. So it's called power method algorithm. There are many other algorithms which you can implement. I have just written one such, not important. Okay, so is there any question in that discussion so far? You can give me feedback. Everything is clear for everybody? Okay. If not, then I'll just go ahead and talk a bit about this graph, Facebook. Yeah. This is, let's assume that this is a Facebook network. So what is this? I connect 1 to 2 if they are friends, right? If 1 and 2 are friends, similarly 2 and 5 are friends, right? 5 and 4 are not friends. So I have made this adjacency graph of, or the friend graph of Facebook. And how much information, what kind of information can I capture through the adjacency matrices of this? So you might have seen when you go to someone's Facebook page, it shows that you have a common friend, right? You know someone who is known to that person. Some common friend it tries to show. So what you can do is you can write the adjacency matrix of this. Adjacency matrix meaning for one, for example, if you take one, in the first row, what will come? So one is trying to 2, 3, 4. So one is trying to everyone. Hmm? So the row that you will write is 0, 1, 1, 1, 1. Row 2. Row 2 is going to be what? The 2 is friend with 1 and 3 and 5. So 1, 3rd and 5th place are going to have 1, and 2nd and 4th place are going to have 0. Okay. Like that, I can write a matrix. So for this particular graph, I had written a matrix. I don't know how to show it to you, but let's do this thing. I have put it on some place where it can actually calculate matrix multiplication. So I'll just make another share. I can't see. Just 1 minute. Yeah. So I'll share something else. So this graph you just imagine, okay? And let me do some matrix computation using the adjacency matrix of this. Let me share my browser. You can see this, right? So this is what adjacency matrix is, okay, for the given graph. Remember, first node, first friend, the first person in the graph had everyone as a friend. Second one, they don't have 2 and 4 as friends, but everyone is like that. Well, 2 is itself, right? So the diagonal is going to be 0 for such matrices. So I have written the matrix, and here the 5 by 5 matrix for which I am going to calculate second power. So let me calculate its second power. It doesn't. No, it's not working here. Let me try it again. No, I'll just write it again. 0, 1, 1, 1, 1, and this is 1, 0, 1, 0, 1, right? 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, and then 1, 1, 0, 0, 0, 0. This is the matrix, and this matrix again it doesn't show. Maybe the sharing mode there is some problem in the processing. Let me just try to. What I'm trying to do is I'm trying to square the matrix. So had it been the in-person interaction, I would have loved one of you to actually calculate it. I'm trying to calculate square of this. Yeah, I'm trying to calculate second power of this. When I calculate, okay, good. It shows 42211, and then 23121, and then 21312, 12121, and 11212. Okay, you can just write it down on your notebook, and I'll go back to the other screen, which is my presentation. I hope you have written it down, and I come back to the presentation. Yeah. So here you can see for this particular matrix, yeah, also on this particular graph. So let's assume graph and matrix are having the same information. It's adjacency matrix. If I square it, then what are the diagonal elements? 4, 3, 3, 2, 2. Right? Those were the elements 10. So can you just tell me what is that 4? What is 4 with respect to 1? What is 3 with respect to 2? In that matrix. So 4 is the number of friends which one has, right? So if you just square the adjacency matrix, the diagonal what you are getting is number of friends which are there. So for 2 we got 3, right? For 5 we got 2. 5 has only 2 friends. So diagonal is going to have the information about friends. And what about off diagonal element? So of course it is a symmetric matrix because here I am assuming that if my right, I have made it undirected graph. So what is the information in the off diagonal? For example, let's say for the first vertex, the third entry was 2. First vertex, the third entry is 2. What's the meaning of that? Actually, that is information about common friends between 1 and 3. So what it says is that 1 and 3, the number of common friends is 2. So who are the common friends? One is this, and other is this 2 and 4. So for 1 and 3, 2 and 4 are the common. So that's a very simple thing. And I would like to give this exercise to you, that if you write down the adjacency matrix, then its first power gives you information about number of friends for all the people in the diagram and number of common friends as well. So ijth row is number of common friends between I and j. So why does it happen? See, matrix multiplication to start with looks like some absurd thing when we learn it in class 11 or 12. It looks like some very random process, like some rows, columns, you just compose them in certain way. But why should that matrix multiplication actually give us information about common friends in Facebook? When I do it in this way through adjacency matrix, maybe that's an exercise you should try to do that. Okay. So about graphs which are arising, I'll just say a couple of words and then I'll stop my discussion. So there was a project in 1930s which was called 6 degrees of separation of the small world project. What it says is that the hypothesis was that if you think of the entire world as a network, there's a network of friends. I know him, and so on. Then, given any two people, say A and B, there is a sequence of 6 friends. So just in 6 steps, I can reach any person to any other person by means of 6 friends. So this is my friend, my friend, my friend, like that. Okay, and that was called small world hypothesis. So we test that hypothesis that time, and interestingly, uh, there is some person, Carl Bunyan. He took the data of Facebook users, 5.8 billion users, and calculated how much degree are we separated by. And he used lots of linear algebraic methods and some methods coming from probability theory. And he came up that average separation of two people is actually 5.73. And the maximum degree of separation within the Facebook group is 12. So that's something interesting analysis over graph. And in maths also we have such graph analysis, right? When we look at our math finite, data, people are always interested in calculating what is their Erdos number, right? If you have co-authored paper with someone and that person has co-authored with someone and like that. So how far are you from Erdos? So one can calculate the math finite data also. Actually, in the calculation, what comes handy is taking higher powers of matrix. Okay, exactly like what Facebook algorithm is. And therefore, there should be ways to accomplish matrix multiplication or the powering matrices in an efficient way. And that's where we have very special types of matrices, right? Certain canonical forms or diagonal matrices are absolutely wonderful. You can immediately raise powers to them. But even if in the simpler form, some kind of Jordan decomposition, maybe rational canonical form, if they are, perhaps you can try to uh, have a better or faster way of multiplying. So I'm just done. See, linear algebra is something which is considered a subject of pure math, but it is actually occurring everywhere, including lot of applied maths and sciences. The differential equation is coming left and right? And in computer science, graph theory, and all that. So that is what uh, one of the famous scientists, Eugen Wigner, used to say. This is unreasonable efficiency of mathematics. Mathematics is efficient to unreasonable extent. There is no way to explain why mathematics is used, but it is used. So unreasonable method. So his statement I'm just quoting and stopping. The unreasonable efficiency of mathematics in science is a gift that we neither understand nor deserve. And linear algebra is certainly one of the examples in the context of Wigner. So yeah, with that, maybe I'll stop and I can take questions. I'm done.
Thank you very much, Amit sir. Anyone has questions for Dr. Amit? Any questions?
Okay.
Okay, there are no
So good.
questions. Thank you very much, sir.
Okay, good.
Okay. Are you saying something? You are on mute.
No, no. So now I think I can go, right?
Yes, yes. Thank you very much.
Okay.
Thank
Sure.
you.